Hello, everyone. Thank you so much for joining us today for our first webinar in our spring technical series. We will be starting in about 2 minutes, so please settle in and we'll be with you shortly. Hello, everyone. Thank you so much for joining us for the first webinar in our spring technical series, a deep dive into PHY architectures for Gen-Z memory fabrics. Today, we're going to have presenters participating: Tim Symons, Associate Technical Fellow with Microchip Technology, James Regan, Physical Layer Logical Expert with HPE, and Dr. Karl Bois, Lead Signal Integrity and System Interconnect Engineer at HPE. Tim, take it away.
Hello, everyone. Thank you for joining us on our webinar. So we'll start today by have a brief overview of the memory fabrics and look at the specific challenges when interconnecting processors, GPUs, accelerators, and memory in a shared fabric. The interconnect characteristics for a fabric, especially when attaching memory devices where you're going to use executable, you're going to work out of executable space, requires you, firstly, the fabric must use memory semantics. So Gen-Z does utilize memory semantics. That is read-write, otherwise known as load-store operations. The transactions are optimized for cache sizes. Again, that's very appropriate, obviously, for processing and ensuring very high performance, low latency transactions. The interconnect to Gen-Z supports memory devices, processors, and accelerators, and memory can be shared between those processors or allocated to a specific device, depending on the workload that is relevant at the time. Now, executing from memory, such as, for example, DRAM, when it's direct attach, has very low, a very consistent response time. If you attach that memory to a fabric, then one of the key parameters that we need to control with Gen-Z is we need to make it very fast and very consistent in its response time. And you'll hear in this presentation quite a few comments, the term latency come up quite a lot. Now, latency in this context is time from initiating the transaction to getting the result. So we'll be looking at low latency and latency jitter. That's variance in that latency time. We'll also look at the PHY architectures for Gen-Z memory fabrics. In order to keep things very high performance and reliable, Gen-Z has adopted the use of Ethernet and PCI PHY technologies. However, we are getting different performance out of those same PHYs, so we'll look a little bit about how we do that. So Gen-Z is a robust fabric. It can be used in a variety of configurations to interconnect devices, and the spatial separation of those devices is very important for a fabric. We want to get memory that can be centimeters away or even meters away. We can build racks or storage elements consisting of memory. Now, that's been done with storage devices before, but this is new. This is memory devices. So the primary goal of Gen Z is to enable memory pooling and sharing across compute engines. So that could be CPUs, GPUs, FPGAs. Often in the application space, there's no single processor type that is optimal for all the analytics that has been done to data. So this mix is very attractive. By sharing memory, we eliminate the time and power consumption required to move data from one location to another. If data is stored in a pool, then processors get allocated access to that data and can operate on it without moving the data. And this is very important for time-critical, large parallel data analytics, such as artificial intelligence and more commonly business analytics today. On the left-hand side, you'll see the guiding tenets for Gen Z. So as a consortium and as a set of objectives, we need to ensure that the protocol and the Gen Z technology is accessible, so it's open, so the specifications are open. It has the performance for memory. It's reliable. Security, with external memory devices, you need to be secure. Flexible, compatible, and economic. We'll step into some of these tenets as we go through the presentation. So Gen Z allows sharing as well as a resource allocation for large data sets to be retained and operated out of memory. This comes with challenges because we now have to meet memory level performance across the fabric. So we have DRAM attached through a switch. Now, transaction time should be short. Processors expect fast responses when they request data from memory. And those transaction times should also be consistent. That term, any variability in the time taken for a response is often referred to as jitter, and you'll hear that through this presentation as well. So latency jitter. To do this, we have to minimize transport errors. Those errors can result in a corrupted data transaction and result in a retry. And that's where this term jitter comes in. It's retrying events that causes change, a longer response time than if there was no error. By adopting and leveraging proven ecosystem elements, Gen Z provides a level of confidence and trust in the ecosystem. We're able to leverage best-in-class technologies, reuse connectors, reuse cables, and use system components that technologists are familiar with and have the reliability of being available at this time. The key difference of Gen Z is in the protocol, the channel characteristics, and how they are optimized for the low latency requirements and high bandwidth requirements of memory and processor attachment. So the question comes about, if we're reusing technology, how can Gen Z be different? How can Gen Z have different interconnect reach and error rates if you're using a PHY that has a certain specification? There are a number of characteristics of that, and you'll hear those through this presentation. One area I want to touch on here is the protocol. So I mentioned earlier we use read-write semantics. So that allows us to have very efficient command structures, very small transactions packets. And then within the transport layer, we divide our transactions into small payloads. We use fit packets, which carry a payload of 32 bytes, and those payloads can consist of commands or data. Those fits, though, can be transferred over one lane, or if you have more than one lane connected to your device, would be striped across those lanes. And so you end up with a very short transport time. Parallel striping can be done up to 256 lanes wide on a single connection for Gen Z. In today's prototypes and demos, we're seeing 4 is a common number, but we do anticipate 8 and 16 lane wide connections being common. Now, connection-based error detection and correction increases the data integrity and gives us faster retry should we get an error. And you'll hear about that in the forthcoming slides. Well, I'll hand over to James. He will now talk about the 5 features, signal integrity steps that we've taken in Gen-Z that allow us to utilize PCI and Ethernet PHYs while improving the reliability and performance of those interfaces to suit a memory-centric fabric. So over to you, James.
Great. Thanks, Tim. So Gen-Z's vision is to provide memory semantic access at all different scales, like Tim was talking about. So you could think of it as a small single socket server all the way up to large high-performance computing systems. And so we have to be able to support very short reach channels, which means components that are very closely connected, all the way up to long reach with long copper cables, for example. And the physical layer is what connects these Gen-Z components together and allows them to communicate over a physical medium, such as traces on circuit boards or copper cables. Next slide. So Gen-Z wanted to enable this topology flexibility, but we didn't want to reinvent the wheel, so we chose to leverage 2 of the most ubiquitous physical layers in the industry out there, so PCI Express and Ethernet. And the 1.0 specification was released in January of 2019, and it consisted of PCIe Express Gen 4, which is 16 gigabit per second per lane, as well as IEEE 802.3bj, which is also known as 100 gigabit Ethernet, which is 25 gigabit per second per lane. Now, the reason for doing this is PCIe is very targeted, and it has a lot of applications for things like connecting up to a memory or a processor, specifically connected to endpoints. And then Ethernet provides longer reach, which means you can have longer traces or cables or more connectors in the channel. And so that provides more of a fabric connectivity. And if you compare the reach, and if you look at the pin-to-pin loss, it's 20 dB for PCI Express. So that means that there's not too much that Gen-Z could do with changing the channel loss requirements there. Ethernet provides more channel loss. You can see 35 dB with FEC, which is called forward error correction. It means that there's enough loss in the channel that you start to get bit flips caused by noise, and those bit flips need to be corrected by the receiver. And so that's what forward error correction does. It sends some additional redundant bits with the data that allows the receiver to correct those bit errors. There's also an option to reduce the channel, and this is what Gen-Z did, is Gen-Z specifies 30 dB as the channel loss, and that means that no forward error correction is needed. And this is important because it lowers the latency of the physical layer. And I'll get into more about FEC latency as we go on. So next slide. In September of 2019, Gen-Z released the 1.1 spec, and so this doubled the physical layer bandwidth. It switched from PCIe Gen 4 to Gen 5, so it went from 16 gigabit per second per lane up to 32 gigabit per second per lane. And on the Ethernet side, it changed the signal modulation. So you can see on the left, bottom left there, that's an I diagram of an NRZ signal, which means non-return to zero. That's what the receiver sees. It sees a bunch of zeros and ones. So the low signal on the bottom would be a 0, and then the high signal above that is a 1. And 200 gigabit Ethernet switched to PAM4, which is a 4-signal level modulation, which means instead of sending zeros and ones, now it sends 0, 1, 2, and 3 symbols. So it's doubling the bandwidth, but as a result, it cuts the signal by a third, or 9.5 dB. So you can see that the size of those eyes, those circles, are now a third the height that they used to be. And as a result, the channel reach is lower, and now Gen Z does require forward error correction for 200 gigabit Ethernet based PHYs. And Gen Z restricts the channel loss from 30 dB down to 20 dB in order to have lower BER, which is bit error ratio. That's the number of bits on a link. And that means that we'll have lower latency in our PHY. As I'll go into more of that in later slides. And okay, let's go to the next slide.
Hi, we actually have a couple of questions relevant to this and the previous slide. The first question is Ethernet better than PCIe? It seems to be the case.
Good question. They are different applications, so it's kind of like comparing apples and oranges, where PCIe is really targeted at a prescriptive space, and it has a use case for endpoint topologies, like I was talking about earlier, where you would want to connect to a processor directly, or memory directly, or NVMe. And then Ethernet has a broader scope, so it has more topologies that it can support. So neither of them is better than the other. You know, PCIe has some advantages because you could make the case that it has a cheaper PHY because it has less equalization than the Ethernet PHY. So there's advantages to both.
Okay, and one other question pertains to this slide in particular. The question is, are the eye diagrams at TX or RX?
This is it could be either, but this one I believe is RX. So the receiver, it kind of depends on how well your receiver is equalized. If you have more errors, you're going to see fuzzier lines, and I think this one is from the receiver.
Thank you.
Okay, good questions. This slide is a diagram of signal to noise ratio, or SNR, to BER, bit error ratio. And this goes to what I was alluding to earlier, where if you get more signal, which means more SNR, then you have a lower bit error rate. So what you can do, and this is what Gen Z did for the Ethernet PHY, is we reduced the channel loss, and that increases your signal, and as a result we have lower BER. Okay. The next slide. This slide is a summary of the physical layers that Gen Z leverages. And I think what's interesting about this table are the two columns on the right, which show raw BER versus corrected BER. So raw BER is just your bit error ratio without any forward error correction, and then corrected BER is BER after correction. And the 200 gigabit Ethernet PHY on the bottom row adds forward error correction, and you can see that on the fabric side there are actually two different types of FEC, and they enable higher, or two different raw BERs, one E-7 and one E-9. So that provides more flexibility for different PHY implementations. So what Gen-Z is doing here is we're giving a lot of different options. We've got PCIe for some applications, Ethernet for some applications, and then even if you want a lower loss Ethernet, which would be the 1E-9, that's a lower latency FEC. So there's a lot of different options that Gen-Z provides that we put on top of the Ethernet spec. Because this spec is not standard Ethernet FEC. It's a Gen-Z specific low latency FEC. Okay. So Gen-Z provides two great options for PHYs and PCIe and Ethernet. So Ethernet provides an opportunity to reduce the channel length in order to reduce errors and FEC latency. But it does not normatively provide a connector. And then PCIe is more prescriptive, like I was talking about, in its application, and it provides a normative connector. So Gen-Z preserves this intent of adding a connector. It has the FTA 1002 connector, and it's really low loss. And there's a webinar about it. So if you go to the next slide, you can see a picture of this connector. And I don't want to go into too much detail about it, but it does provide a lot of application flexibility. And if you are interested in it, I really encourage you to check out that webinar about the connector. So next, I'm going to be talking about FEC latency. So this is the FEC that was added for the 200 gigabit Ethernet spec. So this forward error correction is redundant bits that are sent with the data, and that causes latency on the receiver. So if you look at a read request from the processor to a switch in the diagram on the right, the forward error correction latency is incurred at the receiver because the receiver has to wait for the entire FEC packet, or in Gen-Z we call it a FIT, which means a physical layer digit. It needs to be received before the receiver can process the data and forward that read request through the switch. That's because it has to receive all those redundant bits, determine if there was an error, correct the error, and move on. And for a read transaction, there is also a read response. So the FEC latency is incurred at every hop, and it's doubled because there's a read response. And so just for this one read transaction, the FEC latency gets multiplied 4 times. So when you look at traditional Ethernet, that latency is 100 nanoseconds. And applications are used to seeing DDR style of latency, which would be 100 nanoseconds. So if you have 100 times 4, 400 nanoseconds for your FEC latency, on top of your 100 nanosecond DRAM latency, now you're talking about 400 nanoseconds. And that's not even including switch latencies. So that solution was not going to work for Gen-Z, for memory semantic applications. They're very sensitive to latency. So we made a goal to keep the latency extremely low, and the Gen-Z FEC latency is only 2 nanoseconds. So multiply that by 4, it's only 8 nanoseconds. Compare that, it's only 8% of your normal DRAM access time. So really optimize the effect for low latency. Okay. Another aspect of latency is the latency jitter that is caused by retries. So FEC doesn't correct all errors. There are some errors that FEC cannot correct, and in that case, a link level retry is initiated to redo the request. You can see in this diagram on the upper right, there's a write request from the processor, goes out through the switch, and then there's an error received by remote memory. That's the red line with an X. So the remote memory detects the error. It can't be corrected by FEC. There's a retry request that goes back to the switch, and that write is retried. And so this can be tens of nanoseconds, hundreds of nanoseconds, depending on how long the channel is, because it is a factor of the channel latency for these retry request protocols. And so all of a sudden, the processor now is seeing this increase in latency that it wasn't expecting. And a lot of applications have a sensitivity to latency, and they're expecting normal accesses on the tens of nanoseconds of time frame. And then suddenly, if you're getting transactions normally at let's say 80 nanoseconds, and all of a sudden you get 160 nanosecond latency, that can cause problems in your application. So Gen-Z tries to limit this latency by reducing our uncorrected, our corrected BER down to 1e minus 15. So in that table I showed earlier, the raw BER is 1e minus 7 for the 320-bit fit FEC, and that gets corrected up to 1e minus 15. So 8 orders of magnitude. So it's significant, right? And now you're not getting errors nearly as frequently. That means that if you look at the bottom right, there's a diagram showing average packet latency, and there's a steady state. This is just an illustration to demonstrate what it would look like if you had a retry and you had kind of standard normal packet latency, and then all of a sudden a retry occurs. That would be a latency spike, and the frequency of the spikes contributes to the latency jitter. And so at 1e minus 15, the error rate is less than 1 retry per hour for a 4-lane link. You compare that to PCIe Gen 5 retry rate, which is 1 retry every 7.8 seconds for a by 4, and that's a by 4, and usually PCIe would be a by 16. Okay, next slide. This is a slide showing a comparison of forward error correction in the industry. And things to note are the raw BER that we talked about. Gen-Z is lowering the channel length and reducing channel loss, and as a result, the raw BER is much lower compared to Ethernet. We got 3.1e minus 4 compared to 1e minus 7 and 1e minus 9. And as a result, there's a lot less correction that needs to be done. So it's only 2-bit correction compared to 300-bit correction for 200 gigabit Ethernet. And so I talked about that retry latency that's incurred at the receiver. Gen-Z on that bottom row is only 1.5 nanoseconds compared to Ethernet, which is 51 nanoseconds. And then correction latency, Gen-Z can bypass some correction latency because our errors are so infrequent. But even if you don't bypass correction latency, it's still only 4 nanoseconds compared to Ethernet, 200 gigabit Ethernet of 50 and InfiniBand low latency of 25 nanoseconds. So definitely the latency is a lot lower. And then you look at the final column and you say, ooh, the bandwidth overhead, we do take a hit there, but we wanted to optimize for latency for Gen-Z. So the other effects in the industry are all 5.5% overhead, where lower number is better. And Gen-Z is 18.75 and 9.7. Next slide. So I'll hand it over to Tim for a summary.
Yeah, thank you very much. Thank you. Yeah, so Gen-Z is an open specification. We use working groups, and we have a consortium of member companies. So currently there's over 60 organizations who all have a voice in how the specification comes about. So we were debating about what type of forward error correction and so on was done to create the specifications that James was talking about. And we encourage you to get involved as we move forward to higher bit rates, perhaps look at optical interconnect, and also as new memory classes start coming to market, storage memory classes. So a lot of work ahead of us and a lot of opportunities. So if you're not already a member, I encourage you to have a look at a website, see if it's something you want to get involved with, and get involved. So in summary, Gen-Z creates specifications for high bandwidth, low latency, memory-centric interconnect. And this is enabling the transition in the industry towards memory-centric compute and processing. Gen-Z is delivering a technology that allows artificial intelligence, neural networks, very fast analytics in the application space. So the results of this architectural change are improvements in our ability to deliver time solutions and extract data from large databases. So please get involved if you can. So yeah, perhaps we should move over to questions and answers. Rachel, can you take over this?
Yes, absolutely. We actually have several questions from the audience. This first set of questions, I believe, is in reference to slides 15 and 16. So if you'd like to use those as reference. The first question is, why is the FEC applied at the switch? There's an old principle in computing that error detection correction is best done end to end. I'm curious to know why this doesn't apply here.
Yeah, good question. The errors are so frequent that you will have, you can lose your packet boundaries. So if an error occurs on the length field, which is corrected by or protected by PCRC in the Gen-Z protocol layer, that would make the link go through a resynchronization to reestablish packet boundaries. And so those would happen frequently enough that it would cause significant latency jitter. So those are, and also the packet would be misrouted potentially. So those are some of the reasons why we do correct at the switch receiver. Good question. And we're talking about 2 nanosecond latency, so it's so small that you should do it if you can.
The next question is the FEC standard used by Gen-Z same as the one used by 100G Ethernet, like RS FEC 528.514 or RS FEC 544.514?
It is a different FEC, specifically tailored towards Gen-Z. We actually use a BCH code rather than a Reed-Solomon code because the BCH code is optimized for binary error correction. Because our errors are so infrequent, we only have to correct a few single-bit errors. We also use pre-coding to help mitigate burst errors that are caused by the decision feedback equalizer in the receiver. I'm assuming people who ask the question know what some of these terms are. So no, it is a different FEC, and it's optimized specifically for Gen-Z to reduce latency and try to get the lowest bandwidth overhead as possible.
Great. The next question, I believe, is in reference to the next slide, the one that you're on now. The question is, are the Burr numbers normalized with protocol, Gen-Z, PCIe, Ethernet, lengths of the cable IR drives?
Karl, could you answer this one?
So these curves would actually be protocol agnostic. They are in fact just bits being sent through an additive wide Gaussian channel. And so one might also ask the question, what about NRZ versus PAM4? As per what James mentioned, since we're looking at very infrequent errors, this was for illustrative purposes of showing the trade-off of a better SNR baseline versus a bit error rate, more so than decomposing, let's say, frame loss or coding, et cetera. So they are, these curves are protocol agnostic.
So in following kind of with that train of thought, the next question is, in order to implement Gen-Z FEC in an Ethernet switch, you'd need a custom Gen-Z switch, correct?
Yes, that is correct. And I mean, it's not just the physical layer that's different. It's a totally different protocol layer as well. So you can't just send Ethernet protocol traffic over the Gen-Z switch. It has to be a Gen-Z switch. Yeah.
Great. Next question. This one has a lot of acronyms in it, so bear with me. When Gen-Z uses PCIe 4.0, 5.0 protocol, and when it uses IEEE 82BJ over BS, is it something like for memory, it uses PCIe, and to interface with network, FPGA, it uses IEEE 802? Is this so?
Yeah, so I think the question is, what are the targeted use cases? And yes, I think what the person who asked the question was alluding to is, for PCIe, you would use it for things like FPGA connectivity and NVMe connectivity, whereas your switch-to-switch or your bridge-to-switch connections would use the Ethernet PHY for most cases. I mean, the nice thing with Gen-Z is you get the flexibility. You can do whatever you want, but I think that's where we will see the industry going. Hopefully that answered the question.
Okay, we have a couple more. First is, what impact does the higher bandwidth usage have on Gen-Z transactions?
Tim?
Yeah, I'm guessing this relates to how many lanes you're using. Let's say, if you're transmitting Gen-Z packets across a single lane, then it's just a serial link. And as I alluded to earlier, we expect 4 lanes to be fairly common and more. So when you're sending the transaction across the 4 lanes, a little like PCI works, the packet is striped across the 4 lanes. So you get the bandwidth improvement of having 4 lanes running simultaneously, but also because you've striped it, your transaction time is 1/4, because 1/4 of the packet is going across each lane. So the bandwidth implications here are, the wider you go, the better for higher bandwidth and also faster transaction times across the channel. The trade-off being there with more PHYs and more lanes, you use more power. So hopefully that addresses the question a little bit.
Yeah, and maybe the question is about bandwidth overhead for FEC. And for that, Gen-Z, so I'm guessing that it's also related to how does Gen-Z behave under high bandwidth scenarios? And Gen-Z has a very complex congestion management scheme where it will back pressure from endpoints that are producing traffic that is causing victim traffic to be back pressured. So that's one of the congestion mechanisms it has. It also has deadline timers so that if packets are getting clogged up in the fabric, the packets can be dropped and retried by the requester. So there's a lot of features in Gen Z to support this reduction in bandwidth. Clearly, when we designed the FEC, we wanted to maximize the bandwidth as much as possible, but latency was the higher priority there. So that's why the bandwidth overhead is not as competitive as the other industry standards.
Okay, the next question is, can a Gen Z switch also support standard Ethernet traffic and FEC?
I'll answer that.
Go ahead.
So the protocol is different. So a Gen Z switch would not be using Ethernet protocol. No, you would not use a Gen Z switch to transport Ethernet traffic, or even an Ethernet switch to transmit Gen Z packets, because the protocols are different. Although we use,
say yes,
go ahead.
Go ahead. I was going to say yes, because you could design it to support both protocols, but you'd have to do that, right? You'd have to design your switch to support both Gen Z and Ethernet. So.
Okay. The next question is, are there real Gen Z switch ASICs hardware available, or FPGA-based implementations?
Go for it, Tim. Because you got some slides, I think. We got slide.
We have some slides to show that, yes. So, yes, there are Gen Z prototypes that have been demonstrated. Actually, if you've been to Supercompute or the Flash Memory Summit, you may have seen some of the demonstrations there. Actually, Rachel, should I switch over to show some of those slides?
Yeah, that'd be great.
Yeah, okay. Yeah, so just as backup material, we included a couple of slides. So these are photographs from Supercompute 2019 showing, in this case, we got a rack of 4 different compute servers at the bottom, a shared pool of memory, and a rack in the middle. And all servers are sharing the memory concurrently. The ecosystem is getting quite well established. We already have there's a Gen Z protocol analyzer available from Teleline LaCroix. They were showing that at Supercompute, and so not only is the specifications there, but we've got analyzers, and we have FPGAs that operate as switches, operate as memory controllers. In this image here, we have PLDA. They used ARM processors and then used Optical Interface to connect 2 ARM processors that were sharing memory. And then a slide here where we're bridging from UPI, an Intel interface, to Gen Z using an Intel FPGA with IntelliProp IP there. And then that goes through a Gen Z switch, so that's an FPGA. And these FPGAs are running at 25 gigabits per second per lane, and they're 4 lanes wide. So, this matches that 1.0 specification that James was talking about earlier. And in this particular UPI example, we're showing it, I think it's about, 4 or 8 times faster than if you were trying to do the same transaction to an SSD. So yeah, just showing the power of Gen Z connected memory. And then this final slide is an architectural view of that earlier slide of the rack. So there's a 12-port switch in the middle that connects the servers, and then the servers connect to a rack, and then there are Gen Z memory modules. They look like SSDs, but are actually full of DRAM that are connected to, again, an internal 12-port switch. And so any of these servers can access any of this memory, and that's configurable by a fabric manager. We didn't talk about that on this call, but the whole system is actually coordinated by a fabric manager that provides isolation of data, provides security, enables resources to be allocated and reallocated without having to reconfigure the whole system. So this is a very powerful example of how the protocol and how the fabric runs together. So if there's any more questions, we can take them now, or...
Yep, there is a couple more. So one is, how will the host decide when to use PCIe or Ethernet?
Yeah, it's determined by management prior to link training, so it's known which endpoints are connected. So we have talked about doing a negotiation between Ethernet and PCIe, so that's something that we've considered adding to the spec. So far, no one has requested it, but maybe in later releases of the spec we could do something like that. But right now, it's out of band. Management knows ahead of time.
Okay. There is a question that asks, with improvements in silicon technology, custom ASIC implementations of RS-FEC 528.514 or RS-FEC 544.514 may meet 2 nanosecond latency. So does it make it as good for Gen-Z in the future?
I can have a go at that question. So one thing with the FEC is you have to assemble the entire packet before you can execute the FEC algorithm. So in the case of Ethernet, each of these packets contains 10 bits. So that's 5,440 bits of data you have to buffer before your FEC algorithm can determine if there's an error and correct it. What we did in Gen-Z, these are actually bits. So we're assembling 320 bits before we execute our FEC. So although Ethernet and although technology does move forward, a lot of it is to do with packet size. You have to buffer that packet, receive a packet, buffer it, then execute the FEC algorithm. So it's a combination of buffering and then how fast the algorithm can work. So the small packets of Gen-Z mean that it's always going to have very low latency, and so accelerating the FEC part of this transaction, will also mirror in Gen-Z. So to summarize, I don't think that the packet sizes used in Ethernet, because that protocol has different requirements and that's more suitable for that protocol, that doesn't translate across to Gen-Z. So we don't see them aligning with each other. Having said that, FEC algorithms are well defined, they're well published, and so both technologies will take advantage of technology improvements and performance improvements in silicon.
Okay. There was a question, I believe it was in reference to some of the demo images that you were showing. I can't be certain. But the question is, and the 12P, is this 48 lanes total or 96 lanes?
Okay, let me just jump to that. So 12 ports, and then each of these ports are 4 lanes wide, so it's going to be 48. I think the question is about whether it's bidirectional as well. Gen-Z has bidirectional PHYs, so these would, I believe, are 48 lane switches.
Okay, there was one question, a statement and a question. The error correction specifications were interesting. Can you discuss error detection mechanisms and limits for the various transports?
Not sure I understand that question. Well, I can
Or
So,
is it?
I mean, go ahead.
Would it be related to BCH and its ability to work with multiple errors in a frame, and why we chose BCH over RS?
Oh, yeah, good question. Okay, yep, right. All right, so most of the FECs, besides Gen-Z, use the read SOM, which is the RS, and that uses a 10-bit symbol, like Tim was talking about. So you multiply the number of bits by 10, and the correction is 1/2 of the number of parity symbols that you have. So for 544, 514, there are 30 redundant symbols, which means that 15 of those symbols can be corrected. So that means 150 bit errors for Ethernet. It's crazy. And then they interleave 2 of those FEC code words or fits together, and so now you have 300 bits that can be corrected. And then you compare that to Gen-Z, we're much smaller in terms of our code words. So it's only 320 bits compared to 5,440. And as a result, and our BER is much lower, so we don't have to correct as many. The BCH code that we used is optimized for binary error correction. So it can correct 2 bits for that 288, 260, and detect 4-bit errors, and then it's 99.999% detection for anything over 4 bits. And then for the 320 to 60 BCH code, I believe it detects up to 6-bit errors, and then similarly, it's also 99.9% detection for greater than 6-bit errors. So I hope that addressed the question.
Great. And just to clarify for everyone as well, if we aren't able to get to your question today, or if there is a larger response needed or a more in-depth response needed, we can certainly follow up with that via email. The next question we have is it possible for 2 servers to share the memory, i.e. a shared memory system?
And yes, the straightforward answer is yes. It's not as trivial as just allowing both servers to access one piece of memory. You really want to be coherent if they're literally sharing the same space, so that one server doesn't overwrite the same data in the same memory space. So normally it's partitioned, and so although they're sharing one physical device's memory, you'd share area within that memory. However, it is possible, and it is an objective that 2 processors could share the same memory space. But those processors obviously need to have coherency sorted out very strongly. Gen-Z does not automatically do coherency or manage coherency. It really allows access, and then a coherency layer would be separate communications between these processors. But essentially, the capability is there, and the hooks are there to make it work.
And there is a peer-to-peer coherent op class, which would be used for coherent transactions if the memory is truly shared. So yes, that can be supported with Gen-Z.
Okay, there is another question. It says, eye-opening requirement for Gen-Z. Is it similar to PCIe Gen 4 over 100G Ethernet?
It is, so if you go to that table of BER and corrected BER, yeah, so the the orange table on slide 12. Yeah, so this shows BER, which Gen Z doesn't really specify the size of the eye, but we do specify BER and channel loss. And so for PCIe Gen 4, there aren't any changes, and same with Gen 5. And we just say that the channel loss is the same as the PCIe spec, and the raw BER is also the same. We do make changes, restrictions for Ethernet though, and I talked pretty extensively about those.
Okay, I think we have time for one last question. It's, when do you expect to see the first commercial Gen Z-based servers?
Yeah, I'll take that one. So, obviously we're a consortium, so we're not able to comment on individual product plans of organizations or member organizations. With this Gen Z started in late 2016. It's becoming very mature now, and the concepts are getting well understood. And as you saw from some of the demo platforms there, it's getting quite mature in its technology. So while we can't comment on the availability or likely availability of our customers or our members, it's maturing, and the memory transition, the transition towards memory-centric architectures, seems to be gaining momentum. So that's probably the best answer I can give at this time.
Great, thank you so much. Thank you to our presenters today, Tim Symons from Microchip Technology, James Regan from HPE, and Dr. Karl Bois from HPE. We appreciate you doing this webinar today for us. And just as an informative piece for the group, or for the audience, if you do have questions or would like more information about Gen Z, please visit the website. That's at www.genzconsortium.org. And be sure to follow us on our social media platforms, LinkedIn and Twitter, at Gen Z Consortium for more information and regular updates. Once again, thank you so much to our presenters, and thank you for joining us for today's webinar.